we can move on to Lorenzo's talk about implementing symbol resolution in Starlazu. Just a moment. I need to present Lorenzo. So Lorenzo is more of a freshman among software language engineers at Strumenta, eager to get his hands dirty and build great things. He's passionate about model-driven and language engineering. He also likes to explore other topics from game programming to deep learning. In his free time, you can find him contributing to open source projects, watching The Office, reading camper catalogs, or playing as handball goalkeeper. So thanks, Lorenzo, for being here. And yeah, the word.
Thanks. Can you see the screen properly? Because I cannot see it anymore. So can you see the slides? Yes. Okay. Yes. Thanks, Alessio, for the introduction. I will try to make it as quick as possible without losing details. So as you can see, that title is a bit different with respect to the one that we were advertising. I decided to change it. I like to do it quite often. I was talking about implementing symbol resolution in Starlazu, but I rather switched to semantic enrichment. We will see what do I mean with semantic enrichment and why I decided to change the title. So yeah, that was me. The agenda for today is the following. I will start introducing the context and explain like where are we. Then I will provide a very short definition of semantic enrichment. What do I mean with that? And finally, introduce you to the way we implemented support in our libraries Starlazu to integrate semantic enrichment in language engineering tools implemented using our libraries. The presentation will conclude with a demo where we'll see a small example of how to define the semantics of language engineering component. So let's see the context. As you probably saw in the previous presentation, there was this Starlazu approach that was mentioned. It's our approach to building language processing tools that can be interpreters, compilers, editors, and the general idea is to just build these pipelines as a composition of language processing components. And as you can see in these different examples, there's a recurring task of semantically enriching the abstract syntax tree or the representation of our inputs that we have. And in this presentation, we're going to focus on semantic enrichment. Let's see a clear example. Let's imagine that we want to implement a parser for a very small language. Like in this case, we start from a grammar that in this case is an ANTLER grammar, but could be any other parser generator or even a manually implemented one. We generate our parser, we're happy, and we try to parse and read something for the subsequent phases. So the very first kind of representation, of convenient representation that is known and is used in parsers is what's called the parse tree. Essentially, the source code you can see on the left-hand side of the left of this slide is represented internally as a tree-like structure where we can see the compilation unit, verbal declarations. But there is like the main problem with this kind of representation is that yes, we kind of organize the information, but there's still some noise concerning syntactical things like keywords, operators, semicolons, like separators and things like that. So generally, the next step in this case is to try to refine this tree-like structure by creating an abstract syntax tree, where essentially we just remove the noise, maybe reorganize the information with respect to the expected usage of the abstract syntax tree. Like, I don't know, maybe we plan to need to access some specific features in some specific ways. So we reorganize this information in a way that's more efficient. So at this point, we might say that we've finished the parsing phase of our pipeline, and we are successfully able to take some input text and create a representation that makes our computer code, any other subsequent phases of our tool, able to process and navigate and just query the inputs. But when it comes to things like variables or any other kind of reference that we might have in our input text or source code, it's essentially still text. So when navigating, for example, the variable reference in this AST, we are just able to obtain the information that we're referencing to some variable called x. We don't know whether or not this variable exists, the type of this variable, and many other kinds of information. So the next step in the pipeline, it generally consists in enriching the AST with some semantic information that cannot be inferred from the grammar or yes, from previous steps. So essentially, this is what I imagine to be the semantically enriched abstract syntax tree. For example, in this case, we've done different things. We've linked variable references to their declaration. We have tried to compute the types of each variable and therefore also of the expressions using these variables, also considering the information that we have about binary operations, for example. So we have a lot more information that's essential and fundamental to have when implementing code generators, compilers, and similar tools. So this is what we mean with semantic enrichment. But how does it work? How do we implement this semantic enrichment? Well, in practice, it's not a complex task in the sense like from the perspective of understanding what to do, but then in practice, it tends to become often tedious because of technicalities that needs to be taken care of. For example, the integration of the type computation, linking of names with their definition, which without losing the separation of concerns between the symbol resolver and the type computer. We generally want to avoid executing the evaluation of some rule for computing the type or resolving a symbol if that's already been done for some other reason. And therefore, there are many technical aspects of the implementation that introduce the risk of having a very hard to maintain piece of software, having to take required to take a lot of decisions, technical decisions, and other things. So in Sarlazo, we decided that we wanted to provide support for the declarative specification of both symbol resolution and type computation rules. Declarative in the sense that the user does not explicitly need to navigate the AST and go look for the information, but the user can just define a set of rules possibly also using navigation of the AST, but not necessarily. The user can just define a set of rules, both for type computation and symbol resolution, and many other details are automatically handled by our library. So, for example, we handle the avoidance of evaluating multiple times some specific rules. The API is structured in a way that there's always a clear separation between the symbol resolver and the type computer, while at the same time always also providing you the possibility to use them inside each other. And that's what I define mixed scenario example. So in practice, the first thing before going into a bit more details about the implementation, it's important to understand what is a reference and what do we mean with resolving a reference. So in this source code is called Plin, and it's using Colasso, our Starlasso implementation in Kotlin. And for example, in this case, you can see an AST node representing a variable definition and a variable reference. And in the variable reference, in order to express the concept of referencing to a variable definition, we can use the built-in class reference by name. And during the process of symbol resolution, what we are going to do can be reduced essentially to just setting the target reference in the reference by name for a given feature. So as you can see below, for example, we define the variable definition and we manually define a reference by name and then update it with the correct target. So that is essentially what is going on in the symbol resolution, more or less. So how did we implement the API? So there is a main separation between the configuration time. So let's say the static time when you want to configure the rules of your semantics, type computation, and symbol resolution. And then there's a runtime part. So what is actually used at runtime to perform specific tasks. So the semantics configuration, we of course provide some syntactic sugar in the Kotlin version to make it like easier, but essentially whenever we want to define the rules for our language, what we are going to create an instance of a semantics configuration. And this configuration simply takes a configuration for the type computer and one for the symbol resolver. It's not, we do not need to provide both of them all the time. But for example, if you just need a symbol resolver, you can just provide a symbol resolver configuration, and the same is for type computation. Once completed with the configuration, it gets kind of built and a semantics object gets created, which is the one that you will use in your pipeline. The symbol resolver configuration allows you to essentially define two kinds of rules. Let's say the most important or the simplest form is the scope 4. So essentially, we can define a rule to resolve a given reference or given property in terms of providing the scope where the textual value of the reference should be looked up into. So I will show you definition of the scope class we use in Colasso, but essentially we can provide the scoping information for a specific property. But sometimes we might need a little bit more control. So for example, we might need enough control to represent cases where the scope for a given property is somehow influenced by the scope that is introduced by the evaluation of an element. So for example, if we are in a qualified expression, the scope to resolve the final segment will be intuitively influenced by, or will correspond to the scope that's created from the remaining context. And I will show you an example in the demo. And the scope from method can be used for this kind of cases. So essentially, configurations will consist in scope for and scope from rule definitions. We can use them between each other. We can use them inside the definition themselves as normal methods. Once finished with the configuration, we are going to get back a symbol resolver instance that allows us to resolve all the properties of a given node. A node is a Colasu node, so an AST node, or maybe a node that we built from some line web model. But we can also resolve specific properties for a given node. Yeah, the scope provider is essentially what's used inside the symbol, the symbol resolver. So I like the rules are the same. This is just a technical detail for the moment. For like an implementation detail in the future, it might change. But essentially, the symbol resolver, you can imagine that the general flow is that it computes a scope for some using the scope provider, and then it does other things to actually resolve a given property. Yes, so we represent information in terms of scopes. There is a very basic and ordinary implementation. Scopes are organized into trees. So essentially, we can trees or chains, but essentially we can define a scope with a parent, and in there will be an inside symbol table that is essentially a map linking textual names to their actual symbol. That can be a node or can be any other kind of Kotlin class that you want to define. There are some options that we provide, like ignoring the case sensitivity for some specific languages. But essentially, we can define symbols in a scope to put them in the symbol table, and then we can try to resolve names in case the current symbol table doesn't contain a given name. Then we just go up and look into the parent. So it's the typical mechanism. It is also possible to ask to resolve a given name, but only considering specific types, so what K classes. But yeah, essentially this is the working of a scope. And the scope for rules in the symbol resolver configuration are producing instances of these scopes. The type computers can be defined using a type computer configuration. It's a very, very simple version for the moment. It's not very advanced, but essentially you can define a list of type computation rules for each node type of your AST. You can just define the type that corresponds to the node. And once completed with your configuration, you will get back a type computer that can give you the type for every node of your AST. Of course, in this type computer, you can use the symbol resolver to resolve symbols before actually computing the type. And that's, for example, if you have like binary expressions, or in some cases where you might need to resolve a symbol before. And users, they don't need to handle in any way the combination of type computation and symbol resolution. So for example, loops that might arise in what comes first, should I first resolve or should I first compute the type? This is all internally handled. So it's kind of like we are deciding what's coming before, like egg or the chicken. You don't need to do it. That's okay. Let's see a demo. So I've defined a, oh, it's very dark. Yeah. I've defined a very simple Antler grammar for language. As you can see, we can define modules, we can import or other modules, and then essentially define entities. Every entity declaration can contain a set of features or operations, and inside our operations, we can use two kind of statements. This is just an illustrative example. We can declare variables, and then we can return back values. So it's a very basic language. So the first step is to define the AST that we want to create corresponding to our to our parser. In this case, I created a module AST class, nothing very surprising, except for, as I mentioned before, we, for example, in the import AST node, to handle a reference to a module, we use this reference by name. And in a similar way, when we want to reference the type of a variable in a declaration, we use a reference by name to an entity. And I will show you later how standard libraries can be included so that maybe when resolving the entity, in this case, we consider also some standard entities that we defined outside without being them like part of the AST from the beginning. So yes, we have our AST, reference expressions, constructors. So now the first step in our parser is to take the parse tree that's generated by Antler. So build an instance of that from an input and then transform it to the AST. This is a topic for another presentation, but essentially we provide support for this in Starlasu. And once completed this process, we're going to have our AST with every reference unresolved and no type computed. So now we want to define the semantics of our language. Well, in this demo, everything's defined in the same file. So in a single semantics module, but clearly it can be done otherwise, like instead of defining the symbol resolver configuration inline, we could just pass it. It's just, this is just syntactic sugar for it's essentially a function call where we are passing a lambda, so you can do whatever you want here. In the symbol resolver definition, the first thing that we can notice is that, for example, when defining the symbol resolution rule for operation reference nodes, so for references to some operation, we use the type computer to retrieve the type of something in our process. So we can just use the type computer as if it were some variable, and we don't care about the order of things and how to do them in the proper order. And similarly, the type computer. In the type computer, we can, for example, in computing the type of a reference expression, we can use the symbol resolver to resolve something and then compute the type using the result of the symbol resolution. So there is complete seamless integration between these two components in the configuration. So before I was talking about the two different kinds of rules that we can define. For example, in this case, we are defining the scope to use when resolving a module name in an import. And in this case, I'm using the navigation API. So essentially I'm starting from the import AST node. I'm going to the module containing the import statement. I'm computing all the visible modules from this one, and this visible modules is just a function I defined to essentially get all the other modules existing in the world, and then just excluding myself and then returning it back. And for each of these modules, we can define it as a symbol in our scope. So the result of this will be a scope containing all the modules as symbols. And this is essentially like saying when importing a module, you can import every module that exists in our world, except for the one containing the import statement itself. And this is an example of the definition of a scope 4. A slightly maybe more interesting example is the case of a reference expression. And a reference expression is modeled as I was explaining before. So we can imagine it as the node representing a qualified reference expression, for example. So we have a reference to some symbol, something that's named, and we might have a context which is an expression like a plus b plus c. In that case, the target will be c, and the context will be a plus b, which in turn will be a reference expression, and so on until the context being null. In these cases, when we want to compute the scope where to resolve the target, of course, we need to take the context into consideration. So in the case of a null context, so in case of variable references, for example, or some non-qualified name references, in this case, we are just going to aggregate all the variables that have been declared until the point of this specific node, and we're actually building a chain of scopes. So in this case, the first things that will be visible will be all the variables that have been declared until the point of this expression. If not found inside the scope, then the parent scope is defined as all the parameters of the operation containing this expression. And if not found there, so if we're not referencing a parameter, then finally we can take into consideration features. So this is an example showing how in the rules you can you can create whatever structure of scopes you want to represent the different rules of your language. This depends on your specific language. Well, in the case instead where the context is not null, so when we actually have a qualified name reference expression, then it's very simple to represent the idea that the scope will be computed from the type of the context. So if the context is a reference to an entity that contains some specific features, then in the dot and then target, we want to be able to reference just those features, for example. And we use the scope from rule and in the type from the type computer rule. And the scope from rule can be defined in our case as well. So for example, in this case, we are probably going to compute the type, get back an entity. And in this case, we want to describe what can actually be referenced when having an entity as a starting point. So the scope from an entity. And in this case, I'm just creating a scope where all the visible things are like all the visible features and all the visible operations. If we imagine a language like Java, for example, with visibility modifiers, the features might be just the public ones, or I don't know, any other specific language-specific rule can be defined here. Type computation is essentially the same. The operator expression, for example, in this specific language, this is like a very small language. We define the rule where when meeting an operator, if the operator is an addition and we have two strings, then we can apply it, otherwise not. So we can use it for concatenating, and the result type in that case will be a string. So essentially, the idea of a type 4 rule is to return back the final type of a node, and essentially we can write whatever behavior we want. The only condition is that we return back a node. I told you before that I wanted to show you an example of integrating a standard library, and this is just an example of any other case where you want to integrate external information, like maybe that's stored in a file, maybe that's stored in a database, I don't know, whatever. For example, in the like this example can be seen in the scope from rule that we defined for a module. So when we want to define what's visible when starting from a module, essentially we return back a scope that first contains all the entities inside the module. But then as a parent scope, it also aggregates all the entities that have been imported in that module. And then finally, the final parent scope is contains all the entities that are defined in some standard module or standard library. And this standard module, we can see that its definition is, I just wrote it manually. It's a module, its name is standard, and it contains a list of entities that are just those corresponding to my primitive types. So for example, in the string type is the same one I was using while computing the type of an operator expression. Yes, so let's see an example. I'm trying to move the zoom bar because it's not really. Sorry. Okay. Okay, so let's see a test. In this case, I'm just defining a module where I'm importing another module that we still don't know whether or not it exists. I'm defining a person entity with 3 properties and 2 operations. And essentially, what I want to do is, like in the clone operation, I'm cloning this address that I'm taking from somewhere. And I'm invoking this clone meet operation on the address. And then I'm returning back this new person instance. So the first test is showing that at this point, when we parse the this first source code, this first module, then we are going to have a problem with some things. For example, we will not be able to resolve the address because in this case, we just know about the module person. And therefore, we will also not be able to resolve the type of every variable, like this one, for example. But everything else, yeah, and also some feature and operations accesses like the scribe, but everything else will be resolved, of course, because it's just going to be like local. Then in the subsequent step, what we do is that we parse the module address where we define everything we are using in the module person, and finally everything will be correctly resolved in the person module. So in the one that was not completely resolved before. So if I can just, I mean, the test passed, but I will make it a bit more gradual. So now we are in the at the moment where we parse the person module. We have it, but some references are not resolved. So for example, in this case, we have a reference to the module address, and we can see that is unsolved in the sense that the reference it has a name, so we know that we are referencing to address, but the referred value is null. But on the other hand, if we, for example, look at the describe methods that we have here, this we go to the operations. We have the a reference to the return type, which is the string return type that we have in our standard module. Since the standard module is imported by default without having to like explicitly import it, it's already been resolved at this stage. If we go on until the point where we've successfully parsed the other module, then we can see that that the import situation changed. So the address module is now resolved. And if we go and look at the operations, the clone operation where there were all the statements. So we previously we had this binding statement where the address, for example, the type reference was not resolved. In this case, we have a reference to the address, and it's successfully resolved. And that's the same for every other reference as the test asserts. So we are happy about this. And how is the parser actually integrating symbol resolution? Whoops. So essentially, after after building the AST from the parse tree in Colasso, you can integrate multiple steps, like as many steps as you want to impose. In our case, we are just creating an instance of our semantics, retrieving the symbol resolver and resolving the workspace. So we are we're not using the type computer, but essentially it's already built in the sense that in case some symbol resolution rule would for some reason require the computation of the type, then it would be seamlessly handled by like considering our definition. And so we can just invoke this resolve, and all the workspace will be resolved. The workspace is some workaround that we defined in our case because the API currently doesn't really works well for global scopes, in the sense if you have like symbols defined in separated files, you have to handle that manually. So in our case, what we're doing is that every time the parser gets invoked, we are parsing some like the compilation units and adding it into our workspace or world. You can call it as you want, but essentially, when in this way, running symbol resolution to the on the workspace will actually run symbol resolution to all the modules that we have parsed from the instantiation of the parser object until its end of life. So, and this is actually planned to be introduced in future versions of Colasso that we are currently working on.
Lorenzo, sorry for interrupting you. Can you do it with like 5 more minutes or so? Because
yes, I'm done.
Oh, okay, so I'm sorry. I don't know if you had some finishing slides or whatever.
No, this one, questions.
Okay. Okay. We have a question already from Federico, who asked, can this approach being used? Sorry, can this approach be used at scale on large code bases? Is there any goal to make this incremental?
Yeah, for the moment, everything's kept in memory. So I would say that the memory is the limit. In the future, we're actually looking into solutions integrating like databases or applying some smart criteria to uh, cut out those rules that we keep track if we don't we think we are not going to use it anymore. But for the moment, I I don't know. It's everything's memory.
Okay, thanks. Are there any other questions? Please speak up. In the meantime, I will ask you my question. At one point you briefly talked about resolving access to uh, properties in Java, for example, fields or methods or languages that have access modifiers. So could you clarify how you would handle that case? So, for example, to be clear, when um, the visibility maybe of a symbol depends on who's looking for it. So if it's public, everyone can see it, but if it's protected, you can only resolve it. For example, if you're in a subclass or you're in the same package or stuff like that.
The actual implementation depends on the language, of course, but in the API, what you can do is use the navigation, like navigate through the AST to, for example, um, so, so let's suppose that you are referencing some feature and you're inside the body of a method of a class. That's extending, and the feature is protected, so you're essentially uh, allowed to do it. Uh, all these steps you have to implement them manually, but you can. What I meant before is that, for example, if like when defining the scope, you can define what to put there and what not. So, for example, if you have all the features and you just want to put just the public ones inside the scope, you can do it just filtering on some Boolean property or that I imagine you have on your AST nodes, like public, or on the visibility modifier if it's an enumeration. Of course, you might have like some smart ways to uh, refactor the code so that you maybe provide the feature and your location and do it, but you have to do it manually. I just meant that these scopes can be defined with everything you want inside, and therefore they support you in, yeah, I would say, implement most of the possible resolution rules. In my case, I would just use the navigation, start from the expression, understand where am I, try to analyze uh, the hierarchy of the place I am, always using the AST, and then from there obtain the appropriate features. It can get expensive, but in the like when this in our case, like in the API implementation, we are memoizing lots of stuff. So if you define it inside a rule, that's going to be done just once. Yeah.
Thank you. Okay, we have one last question from Federico, and then we can wrap it up. So the question is, how difficult is to write a symbol resolver compared to writing just a parser? In other words, how much effort does it take?
Um, Well, it depends. I think it depends on the knowledge you have about the language semantics. Because for like when you're writing a parser, even if you don't know the language at all, your objective is to cover the examples that you receive. So even if not in the best way, you still might be able to provide some tree-like structure, making the source code readable to subsequent steps. So you might write an RPG parser, but maybe not be so good in RPG. When it comes to the symbol resolver, maybe you need to write less code if you don't have automated tools or things that is your life like we do for the parsers. So you need to write less code in symbol resolution, but sometimes even especially for legacy languages, it might be very hard to understand to know the complete semantic rules in the correct way. So I would say it takes much more mental effort, but the time is more or less the same as a parser, in the sense a parser is practical in this case. Um, it's more about thinking about the semantics. I don't know. I think it's much easier to get stuck because you don't know where to find the information. Like if you don't know semantics, you cannot just imagine it, I think. I hope.
Okay, thank you. Thank you very much. I think we can wrap it up. So, thanks to everyone who presented. Oh, I see there's one. Sorry,
Oh.
there's one extra question. Okay, we can
Mhm.
handle that. So, do you print out something to see how the symbol resolver is working or not working?
Well, I mean, you can, if you want to do it like, if you want to see it, there are various ways. So in Colasso, we provide support for JSON serialization. In that case, a reference it gets serialized with the name and a link to the result node. So that could be a way. So printing out could be a way in that case. Otherwise, in the this. Oops, whoops, whoops. Sorry. In the test, for example, we have some support to understand whether or not the reference is resolved. I mean, it's just a matter of going to the resolved field of the runtime object and check whether it is null or not. Or otherwise, like during the demo before, I use the debugging tools where you can if you run your test, yeah, and then you reach a point. For example, if you look at the imports, which contains a reference, we can see that the reference is unsolved. So if we open it, we have the name, so the actual reference, the thing we want to resolve, and this referred field that is actually the link, it's null. So we can understand that the reference is not resolved. It's resolved, no. In other cases, we might have, let me see. Yes, in other cases, like for example, the return type of this, which is person, which is here, we can access the reference. We can see that the referred field is set, that is resolved, and actually the referred is this entity 4369, which is probably the same ID of the entity. Yes, of the entity here. So there is an actual link to the AST node representing this entity.
Okay, thank you. No more questions for real now. So let's really wrap it up. So thanks to everyone who uh, gave their presentations, and of course the greatest thanks to the people attending, and especially those surviving up to now. And we've yeah, we made it a little bit late, but not so much. It's still acceptable. So thank you, everyone, and I hope you enjoyed it as I probably forgot to say at the beginning, the panel has been recorded, so the recording will become available in a few days, unspecified, but it will become available. And links will be on the Strumenta community. So yeah, that's it. And I don't know if Federico has other things to say, or
No, I think you said everything. The only things left to say is thank you, Alessio.
thank you.
Yeah, thanks everybody for being here, having us, and have a nice evening.
Yeah,
Thank you.
thank you. Bye.
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 Bye-bye.